resistance. In board exam, there may be question, there may be 2 or 3 mark of question that write about the resistance. Okay, resistance of a conductor. Okay, so resistance of conductor is defined as, it is the ratio between resistance of a conductor, no? Resistance of a conductor, you write this like. Okay. So resistance of a conductor is the, it is the ratio. It is the ratio between the potential difference between the two ends, between the two ends of the conductor to the current through the conductor. Current through the conductor. So that is V is equal to, resistance is equal to V by I. Now this is first. Okay. And we know R is equal to rho L by A. From here, what we found, rho R is proportional to length of the conductor. So more the length, more is the resistance. No? More the length, more is the resistance. And also rho is proportional to 1 by A. So inversely proportional. No? So you can write, more the thickness or cross section of a wire, it will give low resistance. Na? So have you ever seen, we are using such type of thing, we are making thicker wire, means high cross section wire. If the load, means when we try to run any heavy motor or AC, we generally use cables of thick wire, na? Having large cross section, because more current need to be passed for heavy appliances. Okay, more current has to pass. If more current has to pass, every conductor has some resistance. Due to resistance, it will heat up the material, it will heat the wire, na? So if it will heat, again its resistance increases. Okay, so there will be loss of energy. To reduce that loss of energy, we make the wire more thick, we increase its cross section. Okay, so that we can reduce its resistance. Okay, it's generally with day-to-day life we do the same thing, right? For a common small LED light, thin wire is sufficient, we don't need to have any heavy wire for that. Okay, because it draws very less amount of current. Okay, so if current less means resistance will be also less. Okay, is also proportional to temperature. And also it depends upon what we have written before, there is a relation. What is that? Our rho was we have written rho is equal to 2m by n square tau, no, in your square tau. That means resistance is also proportional to it depends on the nature of the material, na? Resistance also depends on nature of material. Okay, so R is inversely proportional to 1 by tau, one thing. So indirectly depends on the temperature. Indirectly, it depends on temperature. So more the temperature, less is the tau. If temperature goes high, tau goes down. If tau goes down, resistance will increase. And number density, R is proportional to 1 by n. So free electron number density, free electron number density. Okay. More the number density, less will be the resistance. Okay. So you know the equation of a straight line, na? Equation of straight line. Line. So y is equal to mx plus c. Okay. In place of y, I'll write, what will I write? I'll write I. Yeah, current. So current depends upon V. So that is equal to 1 by R into V. No. So plus 0. So there is no y intercept. Okay. That means how it should pass through the origin. If I plot for ohmic conductor, it is expected that V and I is generally a straight line. It should pass through the origin. Okay. So what should be the slope? This theta. So slope is equal to 1 by R, that is tan theta. So this is the slope. Okay. 1 by R is equal to I by V, or we can write I by V. Is it correct? 1 by R, I by V. So this type of resistance which obeys this rule, these are known as static resistance. Okay, one is static resistance. And those are not static resistance in case of non-ohmic resistance. In case of non-ohmic conductors, the resistance are known as, okay, means slope. Now the slope will not be a straight line. Okay, slope will not be a straight line. It varies with V. It may have a positive slope or negative slope. Okay, remember, for this it's a positive slope, but non-ohmic conductor slope may be positive or negative. Okay, and that type of resistance is called this type of resistance means varying resistance. Resistance is varies, so R proportional is depends on V. Okay, depends on V. Here R doesn't depend upon V. Whatever the potential difference, R is not going to be. R may be ratio between V and I. No. From the relation, you may say that R depends on the V. No? But the conductor, if I give a more potential difference, resistance will increase. No. We calculate the resistance by this relation, but actually it doesn't depend upon potential and current. These are the two tools through which we calculate. Actually the relation is like this. This is the relation where rho is equal to this quantity. This will decide what will be the resistance, not the voltage or current. Okay. Okay. So those resistance which varies with potential actually depends on the potential. These resistances are, for this type of resistances, means R depends on V, are known as dynamic resistance. Dynamic resistances. So what is the dimension of resistance? Can you calculate? Dimension R V by I. L T. How can you calculate? No, you just calculate. This is V by I. What is V? Pot L. Oh, that is potential. You are talking about velocity. This is potential. This is not velocity. Lt minus 1. Symbol are same. Okay, we use the same symbol, but this is the potential difference. That is work done per unit charge. Nah, I is so what is work done? That is force into distance. Nah, force into distance. Q is equal to IT. Right? Q is equal to IT. So there is another T, so it will become like this. No? So force is equal to M1 L1 T minus 2, mass into acceleration, into distance means I will make L2. No, I will make L2. I is ampere, that is ampere square. T is time. So that is M1 L2 T minus 1 A minus 2. Is it right? I did some mistake. This is T1, no, plus 1, sorry. So if it will go off, it will become minus 3. M1 L2 T minus 3. A minus 2. Okay. So what is its unit? Resistance has unit volt per ampere. It is known as ohm. No, ohm. So if I write 1 ohm is equal to 1 volt divided by 1 ampere. So you can define what is 1 ohm from this relation. If I define, if giving a potential difference of 1 volt to a conductor, if the current through the conductor is 1 ampere, right, by giving a potential difference of 1 volt across a conductor, then if the current through the conductor is 1 ampere, that means the resistance of the conductor is 1 ohm. You can define like that. Yeah. So this way we define its magnitude. Okay. And for and for this is SI units. In CGS unit, it will be start volt by stat ampere. In CGS unit, CGS electrostatic unit, there are two. So one start ohm. Its symbol is omega. This is the symbol. Is equal to 1 stat volt divided by 1 stat amp. So do you remember one relation between stat ampere and ampere? 3 into 10 to the power 9. 3 into, no, 1 ampere is equal to 3 into 10 to the power 9. 1 ampere is equal to, I'll remove this one, I'll write here, 1 ampere is equal to 3 into 10 to the power 9 stat ampere. Okay. And 1 volt is equal to 1 by 300 start volt. Okay. So from here I can write how much? What will be its value? From here I can write 1 ohm is equal to 1 by 9 into 10 to the power 11 start volt by start ampere, that is start ohm. 1 ohm is equal to this much start ohm. Okay. What is the inverse of ohm? 1 by R. That is what? Resistance, that is conductance. Resistance inverse is conductance. Its unit is MHO. Mho. You remember this thing, okay? Similarly, you calculate unit and dimensions of resistivity, specific resistance or resistivity. You try at home. So variation of resistivity with temperature. Okay, variation of resistivity with temperature. Variation of resistivity with temperature. We don't have any direct relation with the temperature, but we know resistivity is just 2m by n e square tau, and we know tau is inversely proportional to resistor. That means resistance has to be directly proportional, no? Tau is inversely proportional to temperature. That gives resistivity is directly proportional to temperature. That means if temperature increases, okay, can you hear? Can you hear me? Hello? Resistivity also increases. Okay. So for conductors, first for conductors, okay, which have free electrons. Okay, free electrons. Okay. If we plot graph between resistivity and temperature, we generally found, suppose this is 200 Kelvin, it is in Kelvin. This is 300 Kelvin, 400, 500, 600, 700, 800. Okay. The curve is not, no, it's not straight line all the way. Above 800 temperature, above 800 Kelvin, it goes suddenly high, and below 200, there is some remaining resistivity in the material. It not goes to zero. Okay, but in the room temperature. So what is the room temperature? It's around 300 Kelvin. 27 degrees centigrade room temperature. What we know by room temperature? Generally, we choose that is 27 degrees centigrade. That is 27 plus 273. If I add 273, it will become Kelvin. So that is 300 Kelvin. No? So above room temperature, or you can say around room temperature, or above room temperature, it behaves like a straight line behavior. Okay, so for all conductors, this happens in mostly all conductors. Maybe this point varies a little bit, but around this room temperature, it has already achieved this straight line behavior. Okay. Okay. So at absolute zero, zero degree Kelvin, 0 Kelvin, but you don't need to write degree, 0 Kelvin. There is some residual, there is some minimum finite resistance. Okay, finite resistivity. Okay, this finite resistivity may vary from different conductor to conductor. That's okay, but it somehow it shows the relation like this. Okay. If rho 0 resistivity and rho t are resistivity of a conductor, are resistivity of a conductor at temperature T0 and T respectively, then we can write resistivity at temperature T is equal to rho 0 1 plus alpha T minus T0. Or simply, if I rearrange, alpha is equal to rho T minus rho 0 divided by rho 0 whole into T minus T0. Okay. This formula we use in coefficient of thermal expansion, coefficient of linear expansion, coefficient of volume expansion. Similarly, this is the coefficient of rho 0. Is the resistivity at conductor at temperature T0? No. Rho 0 and could be at room temperature. Yes, that can be a room temperature. Okay. Or not room temperature, we say at 0 degrees centigrade. We define some temperature 0 degree centigrade. Not 0 degree Kelvin. 0 degree Kelvin. We cannot come to this line. Then if we come below this temperature, then this relation will not going to hold anymore. Okay. So this is the property where it shows a straight line behavior. So alpha is known as coefficient of resistivity. Okay. Alpha is coefficient of resistivity. So how can we define alpha? Now it's change in resistivity. Alpha definition. Okay. Definition. Change in resistivity per unit initial resistivity. You are starting from temperature T0. At that point, your initial temperature at that point resistivity is rho 0, and you are dividing with rho 0. That means per unit initial resistivity. Okay. Per unit rise of temperature. You are dividing by temperature, means you are calculating per unit time, per unit. Okay. This is all about conductors. Maybe it is not in your course how the resistivity varies with insulator. Just remember a relation for insulators. Rho T is equal to rho 0 Eg by Kt. Here are two terms, Eg and T. You don't know these terms. Eg is the band gap. And K is band gap, means energy. You don't know these terms, so better we will leave here. Okay. Just simply I can tell 2-3 things. Okay, if you can understand it, then it's okay. Okay, otherwise you just remember few concepts only. Okay. Band gap means in insulator there is no free electrons. No, there is no free electrons. Only electrons are in bound state. No. So bound state means they are in the valency band, valency cells. Which electrons will get free? The valence electrons. You understand that one? What is valence electron? The last cell electrons. No? So the last cell electrons will have some energy. They have some energy levels. No? And when they will get free, electrons try to conduct what? conduct temperature, they will also conduct temperature, they will also conduct electricity. Those electrons are known as conduction electrons or free electrons. Okay, their energy is known as the energy band they possess. There will be no single energy for the conduction electrons. That could be a multiple energy levels. That is known as band. Okay, BAND, band. Okay, so band gap is the energy difference. Energy difference between conduction band and valence band, VLNC, valence band. Okay, so what happens in insulators? There are no free electrons to conduct electricity, but when we increase its temperature, few valence electrons will get energy and they become free. Okay, they became free. If few electrons becomes free, means they are now eligible to carry a current. Okay, before there is no current, with increase of temperature, free electrons increases, and that's why their conductivity will increase. Okay, conductivity will increase. Okay, but in case of conductors, with increase of temperature, their resistivity increases, but in insulators, with temperature, their conductivity increases, resistivity decreases. Okay. Okay, and this K is known as, you know the word Boltzmann constant? Yes, this K, or we write KB, this is Boltzmann constant. If I remember correctly, it is 1.38 into 10 to the power minus 23 joule per Kelvin. If I remember completely, I am not sure. Okay, KBT is the temperature. So unit is correct. It's correct. Okay. And then we are talking about superconductors. No? Superconductors. I will just draw the graph between them. This is this. It is not exactly line. It drops like exponentially. Suddenly, at certain point, resistivity drops to 0. This T0 is known as T0 is known as critical temperature. Critical temperature of that material. Which material we are calculating the relation between rho and T is the critical temperature of that material. Okay. A specific example of we can say mercury. First, this property was observed for mercury. Hg, its symbol is Hg, na? Its critical temperature is 4 Kelvin. There was an experiment. Okay, first there was an experiment in 1911 by some scientist Kamerlinger. He found that he was experimenting on mercury, studying its resistivity, and by decreasing its temperature. When he just decreased its temperature below 400 Kelvin, he found that mercury suddenly loses its resistance property, loses all its resistance. No? It becomes superconductor, no resistance. Okay. Okay, this we use this superconductors in maglev trains. You know this thing, bullet trains, maglev trains, maglev, magnetic levitation. Magnetic levitation means it will hover, it will not touch anything. Okay, there are many things are there, so we are not reading anything about that. Okay, leave it that one, leave it there for the time. Okay.